Hello everyone, welcome to the next lecture on the real analysis. Today I will explain you how you can solve the problems related to the pointwise convergence of sequences. Myself Dr. Harish Garg, you can subscribe my YouTube channel where you can find the various lectures on the real analysis. Now what we have discussed so far, we have defined the concept of the pointwise convergence in our last lecture, and if I quickly recall that, if you have the sequence of the function fn from say a to r, where a is the subset of the r, and if in order to check whether the sequence is a pointwise convergent or not, you need to prove this sequence is my convergent for each point of the domain. My domain is A. If you prove that the sequence is convergent at each point of their domain, then that convergence is called as the pointwise convergence. If you have a sequence of the function fn, what is the mathematical definition of the pointwise convergence? Then the sequence fn converges to the f. F is also from the A to R. Then this sequence is said to be the pointwise convergent if for each x which belongs to my domain, the limit of the fnx is equal to fx. Fine. Or you can say if the limit of the fnx exists. Fine. If the limit of the fnx is existence, then you can say it's a pointwise convergent. If the limit of the fnx does not existence, then we can say the sequence does not pointwise converge. Similarly, if fn is a sequence of the function which converges pointwise such that fnx is either the continuous, differentiable and bounded, then f may or may not behave the same nature. Fine. What is the meaning of that? If fn is my continuous, then f may or may not be the continuous. If fn is differentiable, then f may or may not be the differentiable. Now, before I directly move on the next topic, let me explain you with the help of the 15 examples so that you can easily understand how you can solve these problems of the pointwise convergence. Look at the first example. Examine the pointwise convergence on the domain R. Function is defined to be nx over 1 plus n square. Now, since my target is to define the pointwise convergent, what will be your target? Your target is to find the limit of the fnx. If this limit exists, then we can say yes, the sequence fnx is my pointwise, otherwise not. Secondly, we can also see what is the domain is. Domain is my R. And if you look about this function, there are the two cases. If x is 0 and x is my non-zero. Why? Because if x is 0, my function is 0. And when x is non-zero, function is my non-zero. So I have the two different cases. Once x is 0, second is x is my non-zero. If x is 0, what is the value of the fnx? Fnx is my 0. So therefore, what is the value of the limit of fnx as n approaches infinity? That is also 0. Fine. Second case, if x is my non-zero, then your fnx will be same. Then we can compute the limit of nx over 1 plus x square. How you can compute them? There are the two methods. First method is you can say it's a infinity by infinity form. So you can apply the L'Hopital rule. So L'Hopital rule means that is a differentiate with respect to the n. Now clearly say as n approaches infinity, this will goes to the 0. Second method, instead of this L'Hopital rule, you can also you can divide the numerator and denominator by n square. You will get this expression. Fine. Now again, if you take n approaches infinity, numerator part goes to the 0. This value again goes to the 0 plus x square. Now since x is my non-zero, so that means this answer will be 0. So what is the case for that? This limit will be, if x is my 0, limit is 0. If x is my non-zero, limit is again 0. That means this is my existence. So therefore, my function is limit for all x. So we can say fn converges to the 0. In this case, this 0 is my f. Hence, Fn converges to the 0 pointwise on the domain R. Look at the second example. Now examine the pointwise convergence of this. Again, your target is to find limit of the Fnx. Now, we have the three cases. If x is 0, if x is going to b, and if x is lies between 0 to b. What will happen if x is 0? Then your Fnx will be 1 over n. Then what is the limit of the Fn as n approaches infinity at 0? If x is going to b, what is the value of the Fnx? This is 1 over b plus n. So what is the limit of this? Again 0. If x is lies between 0 to b, then what is the limit of the Fnx? X plus n. So again you can see this number is my 0. So in all these cases, the limits are my existence. Limit exists. This is also limit exists. This is also limit exists. So since all the cases limit is 0, you can directly say limit is my 0 for each x. So therefore, Fn converges to the 0 pointwise on the domain 0 comma b. Fine. So that's a pointwise convergence. Look at this another example. Now you can see now it's an open interval. So you can't say that x is equal to 0. It is not possible. Fine. Again, your target is to find the limit n approaches infinity Fnx. Can you find the limit of the n approaches infinity of Fnx? So it is n square x over 1 plus n cube x square. Again, it's an infinity by infinity form. Fine. You can apply the L'Hopital rule. So its limit n approaches infinity 2nx divided by 3n square x square. So I can take this calculation. It's a 2 upon 3nx as limit n approaches infinity. So that will be 0. Fine. This is the first method. Second method is you can divide numerator and denominator by n cube. So you will get as x over n and clearly say this limit will goes to the 0. So therefore limit is existence. So once the limit is existence, we can say Fn converges to this limit pointwise on the open interval 0 comma 1. Look at this another case. Again, your target is to check pointwise convergence and your target is to find this limit f of n. Now it's a semi-open interval. So we have the two cases when x is 0 and when x is my greater than 0. If x is 0, what is the value of the Fnx? So clearly say e raised to power 0 1 and into 0 is 0. So therefore, what is the value of the limit of the Fnx as n approaches infinity? So because Fn is 0, which is my existence. Fine. Similarly, when x is non-zero, then your limit will be this case. Now if you substitute infinity, this number will be my infinity. This is e raised to power minus infinity. That is my 0, which is my indeterminate form. So how you can write that? I can write this is infinity by infinity form. Nx divided by e raised to power n x square. Now clearly say this becomes my infinity by infinity form. I can take an x as a common because we need a limit as n approaches infinity. Then I can apply the L'Hopital rule. So this is limit n approaches infinity 1 e raised to power nx square into x square. Now what is the answer of this case? Because x is my non-zero, I can cancel 1x. So 1 over x is outside. Limit n approaches infinity 1 over e n x square. So when n approaches infinity, this limit will goes to the 0. So this is also existence. This is also existence. So my say the function will goes to the 0. Hence the function Fn converges to the 0 pointwise on the domain of 0 comma infinity. Look at this another one. Discuss the pointwise convergence on the value of the r. Again, you have the two cases, because whenever x is 0, your fnx will be 0. So therefore, limit n approaches infinity, fnx will be 0. Fine, that's the existence. If x is non-zero, then you need to compute the limit of fnx, and fnx is my this quantity. So what it will happen, it's a x square divided by under root of x square. This will goes to 0. So this quantity implies x square over mod of x. So x square over mod x is, this implies mod of x. So therefore, you can see that what will be your fx. So limit of the fnx as n approaches infinity will be, when x is 0, this answer is 0. When x is my non-zero, this is my mod x. So therefore, we can say fnx converges to the f, where f is my 0 and mod x, provided x is my 0 and x is my non-zero. And you can see this will converges to the pointwise on the R. Fine. The only concept which needed to the pointwise convergence is limit is existence. That's only. Whether they are equal or not, there is no problem about that. Fine. Or you can write as a mod x is positive or negative as on wish. So this is my equal as the f. So fnx converges to the f pointwise on the R. This again example will suggested you, because this function you can see that it's a differentiable. Fine. But you can see that fnx, this number is my mod x and it is my not differentiable. So, and the same example we have discussed in our last lecture as well. So the pointwise limit is not differentiable at 0, but fnx is differentiable on the complete R. Look at this another one. Check the pointwise convergence or not. Now it's a closed interval. Again, your target is to find this limit. You have the three cases: when x is 0, when x is 1, and when x is lies between 0 to 1. When x is equal to 0, what is the value of the fnx? This is 0. So what is the limit of the fnx as n approaches infinity? That is again 0. That means this is the existence. Fine. Now when x is equal to 1, what is the limit of the fnx? This is my minus 1 raised to power n. So what is the limit of n approaches infinity of fnx? So can you find the limit of minus 1 raised to power n? So you can see this limit does not exist. Fine. Why? Because you can see this limit is either plus 1 if n is my even, and minus 1 if n is odd. And you can see this limit is my not unique. And once the limit is not unique, you can say the limit does not existence. Now since the limit does not existence, so therefore we can say this is my not convergent. So that means this series of the function is not pointwise convergent. Fine. And it is not pointwise convergent at the single point A. So we can say it is not pointwise convergent everywhere on the domain 0, 1. Look at this another example. Consider the function, examine the pointwise convergence, and check about the boundedness of the function. What does the meaning of this? That means you need to check whether the fn is bounded and the function f, that is a pointwise convergent, if its convergent is bounded or not. That's the meaning of second line. But firstly we will check about the firstly pointwise convergent, because it's the open interval, so you can't taken as a 0, you can't taken as a 1. Fine. So the pointwise convergent means that is the x lies between 0 to 1. So can you find the limit of the fnx? What is the limit as n approaches infinity? It is infinity by infinity form. I can apply the L'Hopital rule. So that will be 1 over x. So the limit is my 1 over x. So therefore, and you can see this is my existence. This limit is existence because x is lies in the open interval. So therefore, fnx is converges to the f, where fx is my 1 over x for x lies between 0 comma 1. So fn converges to the f pointwise on the domain 0 comma 1. Now you can check about the boundedness. How you can check about the boundedness? We can start with the fnx of modulus. It is n over nx plus 1. Now clearly say if x lies between 0 to 1, nx 1 over nx is always be less than or equal to 1. Fine. So this number is less than or equal to n. Or you can say, because it's an open interval, so you can write as a only strictly less than of the n. So what does it mean? That means fnx is my bounded function. Fine. But you can clearly say what is my function fx, 1 over x, x belongs to the 0 comma 1, and clearly say this function is my not bounded. Fine, because it's the open interval, so you can't find the upper bounds of this case. But this is not a bounded, hence the pointwise convergence does not preserve the bounded. That means if this fn is my bounded, it doesn't implies that f is also bounded. Okay, look at this another question. My domain is close interval 1 comma 2, and your target is to compute the limit of the fnx. Again, that implies you need to compute the pointwise convergence. So again, it's a closed interval. So you have the three cases: when x is equal to 1, when x is equal to 2, and x lies between 1 and 2. What will happen if x is equal to 1? So if x is equal to 1, it is 1 raised to power 1 is 1. So what is the limit of the fnx as n approaches infinity? That is my 1, which is unique and existence. What will happen if x approaches 2? Then your fnx will be 0. So limit will be 0. When x lies between 1 and 2, then your fnx will be 2 minus x. Now, if x is lies between 1 and 2, then 2 minus x is lies between 0 and 1. So when this number is lies between 0 and 1, if you raise to the power infinity, that number will be by 0. Fine. So you can see that in each cases, the function is my limit is my existence. So you can take an as a function f. When x is equal to 1, the limit is my 1. When x is equal to 2, limit is my 0. When x is lies between 1 and 2, limit is again my 0. Or you can combine this case 1 and 2. You can combine this case like x lies between open interval 1 to close interval 2. Fine. So therefore fnx converges to the f pointwise. Fine. Now check whether the function f which we have obtained is continuous. Clearly say the function is not continuous at the point 1. Okay, look at these two examples. Again, you can see your target is to find the limit as n approaches infinity. So you have three cases: if x is 0, if x is equal to b, if x is lies between 0 to b. When x approaches 0, then what is the value of the fnx? Is my 1. So therefore, limit of the fnx is my 1. If x is equal to b, what is the value of the limit fnx? So this will be my limit. N approaches infinity, e raised to power minus n into b, and b is my non-zero. Fine. So definitely this limit will be my 0. If x lies between 0 and b, then the value of the limit again goes to the 0. So it means for these two cases, you can define the function fx corresponding to these cases. 1 if x is my 0, and if x is my open interval 0, close interval b, this limit is my 0. Fine. So now instead of the three cases, you may consider only the two cases: x is 0 and x is my this case. Fine. So this is my fx which converges to the point. Now again this is a closed interval. So we have taken the three cases. X is 0, x is 1, x lies between 0 and 1. So what is the value of the fnx? If x is equal to 0, that is my 0. So therefore limit of the fnx is also my 0. What will happen of the fnx? When it is a 1, it is my 1. So limit of the fn is my again 1. Fine. For the two cases, both are my finite. And whenever x approaches 0 to 1, so the limit of the fnx is my, what is the limit of this? We all know limit of the x raised to power 1 by n is always 1. So that is the required result. So what you conclude that I can define the fn converges to the f, where what is my f? F has a three cases. If x is 0, answer is 0, and in both the cases is my 1. So I can say open interval 0, close interval 1 is my 1. Fine. So fns converges to the f pointwise. Look at another example. Test the pointwise convergence. Again your target is to find the limit. Again it's a closed interval. I can take the cases 0, 1 and 0, 1. What is the value of the fnx? When x is equal to 0, so first part limit is also 0. When x is equal to 1, what is the value of the fnx? This number is my 1 over n, and the limit of the fnx will be my 0. Fine. Now for the third case, you have to find this limit. Again you can see, if you taken as infinity, axis lies between 0 to 1. So what is the limit of the xn? Xn is my 0, and n is a 0 over infinity, that will goes to the 0. So this limit is my 0. So in each case you can see that limit will be my 0. So therefore fnx converges to the 0 pointwise on the closed interval 0, 1. I hope you can enjoy this session too. We will see the next lecture on the uniform convergence of the sequence. Till then, you can just practice a lot of these pointwise convergence sequences, so that you can easily understand the lecture of the uniform convergence soon. I hope you can like, share and comment on this video. Best of luck students, and don't forget to subscribe my YouTube channel. Happy learning always.